Good evening, everyone. Uh, Today, we are going to talk about how we can utilize machine learning, machine vision, computer vision in the field of smart monitoring and health monitoring of these lettuce leaves in controlled agricultural environments. So, we all know that we are living in the era of machine learning, artificial intelligence, computer vision, machine vision, robotics, artificial intelligence, and much more. So today we are going to discuss about how machine learning, especially computer vision, can be employed in monitoring the health of these plants in controlled environment, right? So right now what happens that people are doing lot of controlled agriculture in like organic manufacturing of mushrooms, or uh, people have different kind of businesses. Accordingly they do their uh, farming. So today we are going to discuss about how machine learning is helping create autonomous systems for monitoring, health monitoring, supervision, and then optimize the resources at hand. Say for an example, if you are cultivating mushroom, I'm taking an example of mushroom in a controlled environment where you have invested millions of rupees or dollars in setting up this complex infrastructures to producing your mushrooms. But what happens that even after setting up this production huge setup, your crops may be getting damaged, or it may be maybe some infections are accumulating over it, or some insects are trying to destroy them. So how you are going to monitor? So what we have been doing since the like medieval age, that farmers are constantly monitoring it. They are investing their time, people, money, resources, then getting the fruits out of it. But now with the advent of artificial intelligence, robotics, UAVs, especially in the field of agriculture, has made it very easy. And today we are going to discuss about such application, how machine learning is helping. So let us start our presentation. So I'll share my screen here. Right. So let me first, I'm sorry, excuse me. Let's first. So I have decided that we will cover this presentation into three sections. First, I will first go to the first of all application part, how this is helping. Then the classical machine learning approach, and then how deep learning works in classifying the computer vision models, right? How we can classify using the computer vision. So, yes, in what are we going to discuss in this project? So, we are going to discuss about the various techniques, methodologies, machine learning models, their evaluation metrics, their performance in real time, right? And we are also going to talk about how we can deploy these trained machine learning models accordingly to, say, edge devices or cloud services, right? Even in UAV systems, how you can deploy them, or some robot systems. So this becomes so let me first start this presentation. Yes. So as I've already briefed you, this how this machine learning computer vision is helping you to create autonomous systems, say autonomous drones which can automatically detect how the numbers of various classes of plants in a row by using line tracking, edge detection, computer vision, this. And it can also classify these leaves into different categories as well. So my project is here is to how we can create such machine learning models, right? And experiment with them. So yes, this, as I've already discussed, that plant disease are cause significant damage to agriculture because you are investing a lot of time, money, resource into it, and if something bad happens to your crop, then it will substantially losses, and it will pose a major threat to your food security and your overall income, right? So it is important that we detect these viruses or virals or weed classes or unhealthy leaves or unhealthy plants early, and identify them, then take proper measures how we can mitigate them, uh, whether can we come up with some autonomous solution. This for such an example, I've added this UAV figure. So this UAV is doing what is, it has identified that this region needs watering, or this region or this particular plant needs watering or fertilization, or it may need to be removed. So your autonomous system can do all this operation, but before doing this operation, the autonomous system must identify, right? So for the identification purpose, there are multiple sensors. For an example, a classical robot might have cameras, it may have lidar sensor, it may have distance sensor, it may have IR sensors. Using those sensors, it can interact with the outside environment and get the information that whether this leaf belongs to which class, whether this leaf or this plant belongs to cauliflower, or this leaf belongs to lettuce, or this whether this particular lettuce leaf is healthy or viral, right? So our aim is to develop some autonomous system. How are we going to develop it? So first of all comes the part where, by taking this input data from the surrounding, you will train your machine learning model such in a way that it can identify, class or classify what is the object present. So there are nowadays there are a number of architectures available, deep neural architectures. Here in this project, I have experimented with both classical machine learning approach and deep neural network approach. Before starting our journey, let me first discuss about the data set at hand. So it will give you a very good understanding about what are we actually dealing with here. So the data set we have received have 8 classes. So you see these 8 classes: back, DML, healthy, PML, and so on. So what these classes have, that these classes have the images of various classes. This belongs to DML class. Then comes the healthy class, where all the healthy images are present. Bacterial class, where all the bacterial images are present, of lettuce leaf, particular lettuce leaf. Then SBL class. So you can see that these are not healthy, they have contamination. You see that these gray features, these black features, right? So yes, but if you visualize that, these healthy images, there are no such features, right? They are properly healthy. There are no gray levels, gray this contaminations or virals or insects that have damaged it. So all the healthy images are there, and rest of the other images are present. One more thing I want you to look at, this SPW class. So this is suffered weed class. This is one of the weed or bush uh, that is also is whenever you are cultivating something, then these weeds will also come out and will try to harm your plant. They will try to take all the sunlight, take all your water resources, fertilize it, and it will not yield you any good thing, right? It will not yield you any money or invest returns. So you want to classify them as well. Maybe you want to remove them, but how are you remove them? First, you need to identify them, right? So first part is to create a machine learning model which can classify any image to these different classes, right? So we have gone through the data set, images, but before training a machine learning model, we need to visualize a lot of things, right? That for an example, whether the data set has sufficient enough classes, whether the data set, how is the distribution of data set, what is the mean brightness, what is the contrast, what is the variance, entropy. So these all factors will come into play. So yes, so let's come to data visualization part, right? So if we look at the dataset summary, as I've already discussed, this dataset contains images from 8 different classes. It includes bacterial, downy mildew, healthy, powdery mildew, septorial blight, shepherd, and viral. For my convenience, what I have done, instead of using this entire name, and I have auto encoded them with 4 characters long. Let us say BACT or HLTY or VIRL or SBL, SPW, right? This way, it will help me to this auto encoding will help me to directly classify it rather than writing this entire long name, right? So I have plotted all these various images, 5 different random images from each class, right? So here we see that bacterial class, these bacterial class have the small pigmented black spots on it. Downy mildew class, healthy class, PML class, right? Then septorial blight on lettuce, what is Cephas pursuit, what is how this is classified as viral, right? And if you try to, if you want to get this dataset, you can visit this link. So this is a Kaggle link. You will be directly redirected to the dataset link itself. So you can visit there. So if you look at the number of images per class, here I have uh, plotted a count plot for number of images in each folder. So the observation tells us that there are a total of 2,337 images and there is significant data imbalance. The class distribution, if you look at the class distribution plot here, it clearly highlights a significant imbalance in the dataset. The healthy and suffered per wheat class has significantly more data point as compared to the rest of the class. So this class imbalance will significantly affect your machine learning model. So you need to take into account as well. I want to tell you something that in my approach, I have tried both classical ML and deep neural networks. The classical ML technique, I have not done any data augmentation or tried to balance the classes. I extracted the data accordingly, but in deep neural network, since they are data hungry, I have incorporated data augmentation, right? So here, when we are discussing this, further we are going to discuss about classical machine learning technique. So there you won't find any technique which will try to balance the class number of classes. But if you look at this DNN approach, there I have done data augmentation to like balance the number of images in each class, right? So this here you see that images are organized into 8 separate folders and each representing a distinct class that I've already told you. Now, if we try to visualize the distribution of height and width, because an image is a 2D pixels of arrays. So it has some height and it has some width. So based on the data set, if we try to visualize what is the distribution of the various height and width, we see that there is a significant distribution, right? There is a significant distribution, right? So the scatter plot shows the spread of images across the dataset. The box plot, it summarizes. Here you on the right, you will see there's a box plot. It summarizes distribution of the distribution and highlight outlier. So this line represents the mean line, right? Though this mean is close to 650 to 630 to 650 is this mean line. We see that they are not distributed like equal. There is not equal distribution along its mean according to number of data points, right? Yes, but why I am plotting this figure, right? The objective to plot this resize dimension is to choose a particular resize dimension based upon the median or mean of the overall images, or it may be based upon the need of the model. For an example, some machine learning model needs the incoming data to be transformed into 64 by 64 pixels or 128 by 128 or 240 by 250, 240 or 640 by 640, right? And depending upon the resize size, the architecture is been developed. Okay, so but there comes also a fact that we must always avoid resizing to a much larger size. Say for an example, if you've taken this image and it may have some patterns over it. If you resize it, those patterns will get elongated, and the correlation between these patterns, say for an example, a bacterial image might have some black spots onto it. So these black spots surrounded by these black spots are in the region of green leaves. So the model will learn this black spot, how this black spot is correlated with the neighboring green pixels, right? And if you try to, what we will do, you have elongated it to say 120 by 120 size picture, you have elongated to 640 by 640. So the feature extraction becomes very this mundane, right? Because the model is not able to because these feature vectors are now sparsed. So you want more your sometimes you want your images to be resized into compact fashion, such that these anomalies or this distribution of other features will easily get identified when it passes through the machine learning model, right? So yes, image resize plays a critical role while fitting your machine learning model, right? So till now we have discussed about our data set, our distribution along the various classes. We have also seen that there exists significant data imbalance. We have also plotted what is the image size versus height, what is the mean, what is the distribution, then how to choose the resize dimension. Now we will move toward classical machine learning approach. In classical machine learning approach, section 2, we need to, since classical machine learning approach needs feature vectors, right? So how we are going to extract these features, then pre-process them, feed it to classical machine learning model or models, then get the results out of it, do validation, get the metrics out of it. So in section 2, we are going to discuss all about this. So let's start, right? When we talk about feature extraction, what happens that, as I was talking about, that say for an example, this bacterial leaf, right? So this bacterial leaf have small dots, or some gray dots, dark spots present on them in green leaves, right? So first what we do, that we try to extract the standard RGB intensity plot. What is the intensity across various channels, and how this RGB intensity will tell us about the image itself, or the features present in the image. So if we look at this, uh, I want you to go to here. Say, so here what happens that I have resized them to a particular path, particular size, 640 by 640, all of the images. I've also resized them here for 245 for 240, and try to plot the RGB intensity plot. So here I have taken random images from all of the different distinct classes and try to plot the distribution of RGB intensity as well as the mean RGB. What I have found out, that in all of the classes, like if you look at the bacterial class, the green channel is above. If you look at the RGB class, the mean green channel is above all of them. If you look at the healthy class, again the green channel dominates. It is at the top of it, average RGB for PML, right? But if you look at these two classes, average RGB for SBL class and the SPW class, here you will see that the mean in case of SBL, what I have found, that the mean of red channel dominates the mean of green channel, as well as in SPW, the mean of red channel dominates the mean of green channel, only in case of these two classes, SBL and SPW. If you look at this as BW class, so the mean is very close, right? But in the rest of them, always you will find out that the green channel is dominating. Green channel is dominating the red channel, right? So I plotted them for 240, resized them all the images to 240 by 250, and randomly tried to extract the mean intensity. So my conclusion, what I have found out, that only in the classes of SPW and SBL, the mean red channel dominates the green channel. So this information will be helpful in classifying them, right? Again, what I have done, I have resized it to 640 to 6 by 640 and plotted the same to look whether there is any change in it after resizing. So what I have found out again, everything, what I again found out that this green channel dominates in all of the classes except this SBL and SPW class, right? But only this RGB mean is not able to classify it into 8 distinct classes. It is easily classifying into it is able to identify SPW and SBL class based on this mean intensity of RGB channel, but it is not able to distinguish between the rest of the 6 classes. So what are you going to do? So in my approach, what I have done, I have created grayscale images out of these RGB channel images. So let's go to some fundamentals. What happens that whenever we look, any image is a 2D image and it consists of red, green and blue channels. When it say an image size is 640 by 640, so each R channel, say if we're talking about RGB channel, so each R channel will have 64 channels, rows and 64 channel column. Similarly, green channel will have 64 rows, 64 columns, and B channel will have 64 rows, 64 columns. And based on this intensity values, if it is 8 bit, to it will be 2 to the power 8. So 0 to 255, total of 256. So entirely red, in a red channel, entirely red will be represented by 255, and this very like almost white will be represented, almost black will be represented by this 0 number, right? So here, by this way, by stacking different layers of RGB channel of 8 bit to the power 8, that is, every channel will have values. Every channel or every matrix element of RGB channel will have something value in range of between 0 to 255. And then these layers are stacked on top of another to create a colorful image. In my approach, what I have done, since we need to extract features out of it, say these features, say in case of bacterial, these black spots or white spots in case of DML, right? So for that, you need to convert them to grayscale images. So here, if you go down in this notebook, that is notebook 1 EDM. So I have converted them from colorful images to this grayscale image. What is the advantage of this grayscale image is that now your image, instead of having 3 color channels, are only having grayscale. That is, the values, if the particular pixel is black, it will have 0, and if the particular pixel is purely white, it will have 255 range, right? Anything in between will be in the range of 0 to 255. By using this technique, what we are going to do is to extract these anomalies in between pixels. Say for an example, if you look at this picture, bacterial picture, and there is some suddenly there comes some black spots in fairly white space. I'm taking example. So what will happen that these black spots and will have some values. These black spots in present in them inside will have some values which will be like different from rest of the neighboring values, and this is how the feature is extracted based on the local features, that is a black spot as well as the how these the location of these features are correlated as compared to the neighboring pixels, right? It becomes very important. So I have extracted them in a grayscale images and then extracted the features. So what are the different features I need to extract, right? So here I also discussed that standard RGB intensity plots is not enough to classify. We need to extract various features such as textures, color channels, intensity, gray level co-occurrence matrices, histogram matrices, and then create a structured data frame using these feature vectors and then feed it to a machine learning model, right? So let's proceed further. So I've already explained you how RGB channel in computer vision helps, right? So these are my observation that green channel mean dominates all other classes channel except SPW and SPW and one more class we have seen, right? Yes, green channel dominates in this SBL class sorry, green channel is below this SPW and SBL class, right? Yes. Okay. So, yes. Now we will move forward to text extraction, text and feature extraction. So, what happens that in machine learning model, we want different kind of features to be extracted from each particular image. So there, in my machine learning approach, what I have done, I have extracted hierarchic features. So hierarchic features are these features are texture based features. For an example, if you try to see a metal, if you take a metal block in your one hand and a rock in your one hand, so yes, the feel will be different. But if you have only visionary sensors, say only eyes, how you can distinguish them? So texture, right? Metal have some metallic luster onto it, some glow onto it, but the rock will be rusty, light absorbing. So based on these texture features, if you have you can like classify whether this is a metal based on the texture features or this is a rock. So yes, so extracting these texture features becomes extremely important in machine learning model, and for that hierarchic features extraction plays a key important role. These hierarchic feature extractions are also used in medical imaging, medical image segmentations. So I'll tell you a brief project overview. I was working on Scangeny last year, or maybe I finished it in February 25. So Scangeny is a medical device which can classify the oral images. So it's a device you can put it in your mouth and take pictures of it, and based on the pictures taken it can classify whether the person has any tuberculosis, sorry, oral diseases. As for an example, it is oral cancer, malignant, whether it is in malignant phase, it is in pre-malignant phase, or it is in normal phase, right? So for that project also I have extracted these hierarchic features and trained our machine learning model. So what does these hierarchic features have? So these hierarchic features based on gray level co-occurrence matrices. So we extract the gray level image from an colorful image and then then convert it to grayscale, then extract this GLCM feature, gray level co-occurrence features. So typically they have 24 values. You can extract 24 GLCM features out of one picture, but the rest I have taken only first 13 value. The rest 11 make the calculation more complex and computationally like it will be becomes very ineffective. So my research during my research I found out that first 13 columns helps a lot as compared to the rest of the 11 columns, which make the machine learning model like introduce noise and biases. So what these 13 columns have? So these 13 columns have represent angular second movement, contrast, correlation, sum of squares, variance, what is the inverse difference movement, what is the sum average, what is some variance, some entropy, and so on. How you can extract this picture, how you can extract this feature. So here is a sample code I have written. So by using this code, so what I am doing here, I am created a first function which takes the image path. It first convert it into OpenCV format, right? So OpenCV works in instead of RGB, OpenCV Python uses BGR channel. So it stacks images first on B, then G, and R. So yes, then what I have done, I have converted from colorful images to grayscale image by using the BGR to grayscale this function and resize it to 240 by 240. And then what I am returning mahotas.features.hierarchic. Hierarchic features we are extracting from these gray images along the by taking the mean, because hierarchic features are calculated in different directions, 0, 30, 45, 90, and by taking out the average of all of them. So yes, this is the function utilizing which I have extracted all of the hierarchic, that is texture features of the images. But this only hierarchic features are not will not play significant role because these have only 13 columns, right? So I wanted my machine learning model to have more features. For that, what I have done, I have created histograms, right? So I've also discussed histograms. What are histogram features? So histogram features represent the normalized pixel distribution across the grayscale image, right? The pixel intensities, that is 0 to 255, are binned into 64 bins, right? So, for an example, you have a picture which is 64 by 64, and what you want to do, you each pixel, if the picture is 64 by 64, so and it is 8-bit grayscale image, what we expect that for every pixel the value will be lying between 0 to 255. If it is pure black, it will be 0. If it is pure white, it will be 255. And then we have created range. Say for 0 to 7, it will be 1, right? If the range, if the pixel value is between 0 to 7, it will be encoded as 1 histogram feature for this vector. If this grayscale image has, say for an example, pixel value of 5, so it lies in between 0 to 7, it will have 1. But if some pixel value have in range 10 to 12, so there may be some different histogram bin, right, from 8 to 16, then on 17 to 24, and this way various histograms are created and then auto encoded them. So I've wrote this function how you can extract this histogram features here. Apart from that, I am also calculating this mean brightness, because I have also found out that there is significant changes in RGB channels for various classes. So this mean brightness will help me for my model to learn. So yes, these are the things we have extracted. First, the hierarchic features. Second, the mean brightness. Third, the histogram features, right? Right? So these extracted features, that is the brightness, textures, histograms, serve as structured numerical input. So by extracting these features, we want our data frame to be in a structured manner so that we can feed this structured data frame in this particular manner, whatever the model expects, right? So we need to model your training data according to the need of the model you are experimenting with, right? So yes, here you see, by extracting all these features, I've created this data frame. What this data frame has, if you look at the column, it will have the class name, that whether it belongs to PML, SBL, healthy, or whatever class. What is the name of the image, if it is bacteria 1, bacteria 2, viral 3. It will have the mean brightness as its first column, then 0 to, then texture features 0 to texture features, texture 0, texture 1 to texture 13, and 64 histograms, like from histogram 0 to histogram 63. So in total, it has total of 80 feature columns, or you can say 80 feature dimensions based on based on which it can classify, right? So we have created in such a manner. But out of all these 80 features, only 78 are required, since class is a target value. Image name is something irrelevant. We will drop this when we proceed further, right? Let's move on. Yes, I was talking about this mean brightness, how it is important, right? So first of all, I thought ki this RGB channel, there is not significant changes in that. But later on, when I plotted the brightness distribution, I see this violin plot represent this violin plot, that is the probability distribution of brightness, tells us that the mean brightness for all the classes are different, as well as the distribution is symmetric. But only for the case of SPW, it is not symmetric, I found out. So we can use this mean brightness as one of our feature parameters for our machine learning model, right? So yes, I have also written this observance. We can see from the violin plot that the distribution of mean brightness for this SPW class is skewed, while rest of the classes are almost showing symmetric mean brightness. Mean brightness feature will significantly help the model to learn, right? From this box plot, you will also see this is also called whisker plot. From this whisker plot or box plot, you will see that this healthy class might have some outliers, 10 to 12, I've calculated. But for this purpose, I have taken it as it is, not done any kind of dropping the features, because the data set itself has very limited number of data set while fitting. So yes, And I believe these number of outliers are very small. This will not cause any dramatic change in machine learning while the model is learning, right? So for this purpose, I have assumed that this will not cause any significant change because of this limitation in data size, right? So till now we have extracted all the features, explained all the features. Now, before training our machine learning model on this feature data, what we need to do is look for principal component analysis, feature independence, and feature engineering. What are these? So whenever we extract such features, we want to look for collinearity, whether or not some features are linearly correlated or is really linearly dependent on other feature. If such is the case, then the model will be prone to overfit. Then it may not learn from those features accordingly, because since if there exists a strong collinearity, then the model will overfit. The model will not perform better. It may fit good on the training data. It may not perform on the test data itself. So you want to remove such features which are highly correlated. For that, what we do, we plot correlation heat map, right? So yes, as I was talking about why feature independence and correlations are important. So how you calculate this correlation coefficient? So that you can plot sns.heatmap. Okay. So you see this here, correlation coefficient heat map. As I was already talking, it is suggested that we do not feed or train our machine learning model on features which are highly correlated, right? So you can plot this correlation heat map. What it does, it tries to calculate the correlation coefficient. What is correlation coefficient? You can Google it out. It tells us how much one feature vector is linearly dependent upon the other feature vector, right? So you can learn by clicking on this link, correlation coefficient heat map. You can directly go and look at how it is calculated. Mathematical Intuition, Wikipedia is a great source to learn about it. So what does the correlation coefficient heat map does? So it helps detect the highly correlated feature that provide overlapping information, allowing you to drop one to simplify the model without losing its predictive power. Yes, we found out the above heat map tells us there is some strong correlation among the hist features, right? So before that, I'll tell you that we expect strong collinearity along the principal diagonal of this heat map, right? So that's why you are seeing this very the dark red line across the principal diagonal. But no need to worry, we expect such high collinearity across the principal diagonal. But if you look at the rest of the matrices, you will find that there is no such high strong multicollinearity, right? There exists some collinearity in between his feature 40 to his feature 59 in this range, but that is also not too much. We can take all these features directly and do feature scaling and then put it in our machine learning model, right? Hmm. As I was also talking about this collinearity, one more technique is to do principal component analysis, or TSNE analysis. So what does TSNE does, right? So till now, we have extracted various features such as histogram features, mean brightness features, GLCM features, texture features, that is. And then based on these features, what does TSNE do? Based on these features, TSNE creates a probability distribution in 2D space or 3D space based on the 78 column vectors, that is texture, brightness, and all of this. It creates a 2D or 3D space on which, based on this feature vector, it will try to cluster the various components. So whatever feature vectors we have extracted till now, I have already discussed it with 2 slides above. So T-distributed stochastic neighbor is a statistical method for visualizing the high dimensional data by giving each data point a location in a 2 or 3-dimensional map. It is based on a stochastic neighbor embedding, right? So what it did, it construct a probability distribution over pairs of high dimensional objects in such a way that similar objects are assigned a higher probability. Similar objects are assigned a higher probability. So according to the feature vectors we have extracted and TSNE distribution, it clusters, right? It does well in clustering this SPW class. If you look at this legend here, so it does in clustering this SPW class and healthy class better, but rest of the class it is not able to. It fails to classify this viral class, PML class from the healthy class. So if you see the distribution here, so yes, TSNE does well in clustering the SPW and healthy class, but it fails to cluster or classify between healthy, viral, SBL, rest of the classes. So yes, till now we have visualized what are our features, whether they are strongly correlated or not. There exists some multicollinearity or not. We have looked at its heat map as well, TSNE plot as well. Now, moving further, we will discuss about how this extracted information can be used for machine learning model, right? Feature scaling. Yes, feature scaling plays a great important role because if you look at the data frame, some of the feature vectors, if you look at the data frame, let me go 2 to 3 slides above. If I go here, you will see that some of the feature vector like brightness are of the order 10 to the power 2, texture are of the order of 10 to the power minus 6, texture 1 is of the order of 10 to the power 2 to 10 to the power 3. So yes, as well as GLCM features and others. So the order of the values or the features are significant different. So if say for an example, one of your features is or are of one of the features say texture 0 is of the order of 10 to the power 3, while texture 1 is of the order of 10 to the power minus 6. So if you take the cumulative ratio of what is the comparison of order, it is of the order of 10 to the power 9. So when you try without when you fit your model without this standardization or normalization, what does it do? It The model will have bias. It will learn significantly better from one of the features vectors more as compared to rest of them because the scales are different. So before fitting, you want your model to be standardized or normalized. In this case, what I have done, I have used standard scaler to standardize the data points and then feed it to machine learning model, right? So this is my classical ML model space and hyperparameter space. So during training, I have experimented with various model like support vector classifier model, various tree-based models such as decision tree, random forest, extreme gradient boosting methodologies, models, and different hyperparameters. Say when we try to fit the model, so it will need some hyperparameters. Say for an example, when we are talking about gradient descent or linear regression, there is some parameter called this this learning rate, some weight decay parameter, some momentum parameter may be there, right? In these parameter support vector, so after during training, I have experimented with different C values, different kind of kernel, different decision functions shape. Similarly, for random forest, different kind of estimators, criteria, depth, nodes, estimator, learning rate for, and then fit the model. After fitting the best fit hyperparameters, what I have found out is that, excuse me, so support vector SVC model performs best with C value of 10. Lower C value represents smoother distribution. There's a like C value of 10 is a very significantly high value, right? Then decision, what is the decision function? What is the kernel RBF or OVO, whatever it is. In terms of for random forest, what I have found out the best fit hyperparameters is when it try to split based on entropy for maximum depth of 10 and number of estimated used are 20. Similarly, for decision tree criteria, best criteria for splitting is Gini. Maximum depth is 10, maximum leaf nodes are 10. Extreme gradient boosting, so it performed best with learning rate of 0.1, maximum depth is 3, and then number of estimator 200, right? So till now till now what we have done, we have extracted features, standardized them, created a model and hyperparameter space, feed the train data to it, and like evaluate it. But one more thing I wanted to mention is that For this machine learning operation, classical ML approach, I have used 80% of the images for train and rest 20% is for validation or testing, right? Yes, after model fitting, then comes the part of model evaluation. Which model performs better as compared to the other model? What are the aspects on which it is performing better? What are the various metric parameters? Precision, recall, F1, ROC, AUC, confusion matrix. So all this comes after this model fitting. So we want to visualize them as well, how our model is fitting. So let's take a look at that, right? So till now we have in classical ML approach we are experimented with four model SVC, RF, decision tree, and XGBoost. RF represent random forest. So as a machine learning engineer, we experiment with different features, different versions of data set by extracting different features out of it. We experiment with different model architectures, whether it is classical ML or deep neural network architecture, then try to evaluate it on a test set, try to get the metrics out of it. So this all this comes under, and when new data comes in, then we need to again change some parameters, again go for training, deployment. All of this comes under MLOps, machine learning operation. So for model tracking, model evaluation, there's one very great tool which machine learning practitioners usually do, are there such as MLflow, AutoML. So these provide a graphical user interface, web-based graphical user interface for model tracking and evaluation. If you want to like visualize how my various models are performing, what you need to do, you can go here. So I am already running. Just close this. So the virtual environment I am working with is leaf classifier. I will activate first this environment. Yes, it is activated. Upon activation, the virtual environment name will be in front of it. And then to launch MLflow, since I've already experimented and all the logs are there already inside here, ML runs. So if when upon hitting enter, it will launch the launch the MLflow user interface on a local host. So here it is on port number 5000. If you go here, you will you can see this kind of user interface. You will go below multi-class. Here I have experimented with different models. So yes, here it is. So if you look at this, here are different models. I have trained it for multiple times, but just visualize these models, right? XGBoost, DT, Random Forest, SVC. If you look at if for comparison, you can do direct comparison here. You can look at accuracy. So in terms of accuracy, XGBoost and XGBoost performs better as compared to rest of the DT, Random Forest, or SBC. In terms of F1 score, in terms of precision, in terms of recall, in terms of ROC, receiver operating characteristic, AUC value, right? It is close to 0.99, recall is 0.95, precision 0.934, F1 accuracy. So from here you can get all the detailed comparison metrics, right? You can even plot them, right? So for comparison here, you can plot them, look into it, what are the results. So yes, you can do all the things, models, experiments, different models are there. So every model has the specific run ID. From using that run ID, you can fetch that model, create a FastAPI app at the back end, which can call that model from that space, and then use it on the front end, whenever whatever technology you are using, Streamlit or JavaScript based technologies, you know, right? So yes, MLflow is a great tool for experimentation and model tracking. So here we found out that the XGBoost model performs better in terms of rest of the models, right? Okay. But during my research, what I found out that there are other models as well. Now, first of all, sorry. During my research, I have found out voting classifiers is one of the techniques, ensemble machine learning techniques, which will eventually increase the performance of classification. How it is, we'll also discuss it. Let's first look at the evaluation metrics and comparison for all the classical ML models I have experimented with. So confusion matrix is a great example of it. Do not look like suddenly accustomed ki why only two values are there, because there is a significant data imbalance as we have already discussed it. But still it is classifying. These classical ML models are classifying very nicely on basis of these two classes, healthy and SPW, because these two were dominant classes, right? Right here you see. And one more matrix is important, since ROC, since this decision, this confusion matrix does not give us a good idea about how the model performs on based on the true positive and true negative. So one more plot is there, is called ROC, receiver operating characteristic curve, right? It is plotted against true positive against true negative. So ideally what happens, you want your learning curves for different classes to be above this dashed horizontal line, right? You want your machine learning model to be the learning curve for individual for each classes to be above this uh, diagonal line. So for all these models, you see there, for an example of SGC and XGB, SVC and SGB, the ROC curve looks very fine, very promising. But in case of random forest and decision tree, you will see that these curves are getting closer. These curves are getting closer to this reference line. In case of DT, what we see that there these two classes while training are below this horizontal line. So if we get predictions from using this decision tree model, the model will not give the like promising results. By looking at this ROC curve, we can say that, right? So in conclusion, what we can say that SVC and XGB model performs fine, performs best as compared to all the rest of the models. And on when compared with SVC and XGB on the basis of F1 recall accuracy as well as ROC AOC values, XGB outperforms rest of all the models. Extreme gradient boosting model outperforms all the classical ML models, right? Hmm. So I have experimented when I was doing this project. I was researching. I found out there's one more approach called voting classifier. What does voting classifier do? Right? Voting classifier is an ensemble method. It's an ensemble machine learning technique that combines the prediction from multiple classes. It will take the predictions from multiple classes, and based on hard thresholding or soft thresholding, it will cast out its vote, right? So here I have also written, right, different types of a classifier can perform either hard voting, whether the predicted class is the one that received the most votes, or soft voting, the predicted class will have the average vote from the different classes, right? So the voting classifier report, here you see that voting, I want you to just ignore for the time being, ignore this support column. Uh, if you look at this voting classifier report, we see this here is all the class or class name numbers auto encoded. Then the precision values, what is the recall, F1 score. We find that class number 4, 5, class number 4 has precision of 1, right? Class number 2 has precision 0.93. And from here, total accuracy, if you look at the total accuracy, it is 0.96. That is very promising result, right? Total accuracy is 0.96. Weighted average 0.94. The voting ROC, AOC value is 0.9938. That is very close to 1. That is very good result. That is a very promising result using the classical ML models without data augmentation, right? Uh,